Hello, this is Ligaya from Boost Revision, and this is our Year 13 chemistry clinic looking at the unified chemistry paper from 2018 to give you guys practice on approaching these unified exam questions, which are designed to bring different parts of the course together in one question, so that you have to draw your learning from different topics and kind of link your understanding together. So this session is sort of being based on the assumption that you've finished learning your course. From what I can tell from those students who are at AAT, your teachers have told me that you have finished the course and that you've got an assessment next week. So I'm hoping that this session is going to help you guys to prepare for that session. Hopefully you might have received my email yesterday and had a go at some of these questions yourself, so that you've challenge yourself to see whether you can answer these questions, and then we're going to go through the answers and how I would work through them to make sure that you've kind of got a good idea of how to approach questions, perhaps how to structure them, how to think about some of these complex questions. So without further ado, I'm going to share my screen with you and the Unified Chemistry paper from 2018. Whether or not you've actually seen this paper, hopefully this session is still going to be useful for you. Ideally, I'm hoping that you will have had a go at doing these questions, but if you haven't had a go yet, then please feel free to have a go as we go along. And I'm just going to sort of talk you through what I would think about as I approach these different questions. So the first question is looking at elements in the first 3 periods of the periodic table. So you want to make sure you have your data sheet handy, because that's really going to help you to sort of reference what you need to be asking about. So I would always highlight that first bit there that's reminding you that we're looking at just elements in the first 3 periods of the periodic table. Select an element for the first 3 periods that fits each of the following descriptions. The element that forms a 1- ion with the same electron configuration as helium. So now the element that's actually the answer here doesn't usually form a 1- ion. That's going to add an electron, and once its electron has been added, it's going to have the same electron configuration as helium. So if you look at the periodic table, this has got to be something that is next to helium and just 1 electron away, and it's got to be hydrogen, because hydrogen has 1 electron. Normally, if we add an electron, it's going to become H-, which I know is not really normal, but that H- ion will have the same electron configuration as helium. So the answer here is hydrogen. You could write H or H2 as well. Those will all be fine. Next, the element with the highest first ionization energy. Now, I think this one does sometimes stump people, especially because we don't normally look at the trends in ionization energy across all 3 periods. You will have seen it before, but normally we're comparing against just period 2 elements or period 3 elements. In this case, hopefully you may remember that if we look at the trends in first ionization energy for all the elements from H to AR, it starts up relatively high, H and then HE, and then it jumps down because as you go down a period, we've got more shells, more shielding, and larger atomic radius. So the electron is further away from the nucleus. So the further down the periodic table, the easier it is to remove, therefore the lower the ionization energy. And then it keeps going kind of like this with this pattern, and goes down again and then repeats the same kind of pattern. So actually the element with the highest first ionization energy is that element there, which is the second element in the periodic table, and that is helium. Okay, so helium, or you can give the symbol He. Right, the next one, the element in the period 3, which has successive ionization energy shown below. We've got first ionization energy of 738, 1451, 7753, and 1054. So what we're looking for here is something in period 3, and what we want to identify is which group it is in based on the jumps between these ionization energies. So this jump is about 700, this jump is about 6,000, 5,500, something like that. So that's quite a large jump compared to 700. And then this next jump is just over 2,000, maybe 2,200 or 2,300 or something like that. 2,000, yeah. So I'd say this is the largest jump, which tells me that this must be the element that's in group 2, because the biggest jump is between the second and third electron being removed, which means that electron must be being removed from a shell closer to the nucleus. So we've looked period 3, that's this row here, group 2, that's that, so we've got magnesium here. Okay, and I'm just going to clear this so that we don't get too confused for the next time. So magnesium, an element which forms a compound with fluorine that has octahedral molecules. So different ways you might think about this, maybe you just remember the most common octahedral molecule, or you might want to think about what the shape of an octahedral molecule is. Let's call this X, and we're going to have a shape that looks something like this. So we're looking for, if you can't remember off the top of your head, we're looking for something that can create 6 covalent bonds around the outside to form an octahedral molecule with F in this case, because it's told us that it's reacting with fluorine. So in the actual fact, the answer is sulfur. The compound would be SF6. So if you didn't remember this off the top of your head, it may be a good idea to go back and revise your shapes of molecules and examples of the different shapes of molecules, because this SF6 is the main example of an octahedral molecule shape. And so hopefully for many of you, if you've done your revision, you will have been able to sort of recall this quite quickly. But if not, just use the shape to kind of give you some clues. If it has to make 6 covalent bonds, then it's got to have 6 electrons in its outer shell, and sulfur actually has this unique, not unique, but unusual property of being able to expand the octet, which means it can make more, it can have more than 8 electrons in its outer shell. And that happens often with group 3 or below non-metals, which can actually share as many electrons as they have in their outer shell. So you can see this with sulfur, you can see this with phosphorus, with chlorine. It's relatively unusual, but basically period 3 is close enough to period 4 that actually the 3p electrons can actually expand into the 3d subshell, which is what's called the expansion of the octet. So that one was sulfur. Cool. An element which reacts with water to form an acidic solution. Okay, so here we want to think about, okay, well, what elements will react with water or even dissolve in water, and if they do, which ones will form an acidic solution. So if you have no idea at all, the first thing I would do would be to try and think about what things dissolve in water, and hopefully you'll remember that metals don't dissolve in water at all. So basically everything in the metal side is completely out. So we're looking for things in the non-metal side of the table here. You may remember that non-metal oxides form acidic oxides. So now we've got to think about which of these non-metals may dissolve in water to form acidic solutions. In actual fact, sulfur and phosphorus don't usually dissolve in water. Oxygen doesn't dissolve in water to form an acidic solution. And you may be able to sort of, if you can't remember off the top of your head that halogens do form acidic solutions, then you may be able to think of things like, for example, HCl or hydrogen fluoride, hydrogen bromide. These hydrogen, obviously HCl is hydrogen chloride or hydrochloric acid. So hopefully if you can kind of start to think out of the box a bit, if you weren't able to just remember that halogens do produce acidic solutions, then you could think, oh, well, hydrochloric acid is an acid that I know about, so perhaps chlorine might be a good guess, and chlorine or fluorine would be the right answers here. Cl or F, and just as I did actually circle bromine there, but obviously just remember that you're looking just in period 3, so we're looking just up until argon as the end point for our questions here. So the answer there was fluorine or chlorine. Okay, the next one, an element X which forms a compound with hydrogen XH3 with a molar mass of 34. Okay, so this one perhaps a little bit more difficult, but hopefully not too bad. So XH3, the molecular mass is 34. So we know hydrogen is 1, so we can take that away, which means X is going to have a molecular mass of 31. So we're going to look on the periodic table and see what has a relative atomic mass of 31. We can see it's phosphorus. So that's the answer there, phosphorus. Okay, an element which forms a compound with hydrogen in which the element has an oxidation number of -4. So if this element has an oxidation number of -4, then the hydrogen is going to have its +1, which is always takes priority anyway. So it's going to be something XFF4. So this hopefully gives you a clue that it's going to be something that's in group 4. And again, it's got to be in group 4 and in the first 3 periods. So it's going to be either one of these two. In fact, both of them would be allowed according to the mark scheme, but they're looking for you to suggest carbon, because carbon is more commonly formed as a compound with hydrogen in this way. You know, if this X was carbon, then this would be methane CH4. So silicon would also have been allowed because potentially it could form a compound with hydrogen with that oxidation state. Remember that in this case, hydrogen would take priority. So even though you might think that sometimes group 4 has a +4 oxidation state, it can also have a -4 oxidation state. So just keep in mind that hydrogen would take the priority according to the priority rules of assigning oxidation states. Okay. The element which has a density of 1.33 times 10 to the -3 grams per centimetre cubed at room temperature and pressure. This one is again slightly harder, still just for 1 mark, but hopefully if you can think about where density comes from and the fact that it's told you room temperature and pressure, that should give you a clue that this means that the volume of this is going to be 24 decimeters cubed, because the volume of any gas at room temperature and pressure is 24 decimeters cubed. Now, it hasn't specified that it's a gas, but because it's talked about density and room temperature and pressure, that's a good clue that it probably is a gas. So we're looking for a gas with that density, and we're going to assume that it's got that volume, 24 centimeters cubed, because we've been told it's in room temperature and pressure. So we're going to take mass equals density times by volume. Now, this is strictly a physics equation. It's not really something you're supposed to, you need to learn for your chemistry exam. But having said that, if you look at the units of any number you're given, that gives you a very good clue of how you've come to calculate that number. So density, the units of grams per centimetre cubed, which means density must be mass divided by volume, because mass is in grams and volume is in centimeters cubed. Okay, now remember that we've said decimeters cubed up here, so that's going to actually be 24,000 centimeters cubed, so make sure you make that conversion as well. But hopefully you can see how I've got to that mass equals density times volume calculation. So we're going to do the density 1.33 times 10 to the -3 times by the volume 24,000. And that gives us 31.92, or if we round it up, it goes to 32 grams. And so this is telling us that a mole, we said 1 mole because of the 24 decimeters cubed, 1 mole of this substance will have a mass of 32 grams, and that, hopefully you remember, that is equivalent to your relative atomic mass, so or relative molecular mass in this case. So looking at the periodic table, hopefully, or maybe you might even remember from memory, the element sulfur has 32.1, but it doesn't exist as a gas. So what we're actually looking for is oxygen as an element in O2 in the molecular state. So oxygen has a molecular mass of 32 because it's O times 16 times 2 gives us 32. So the element is oxygen. Okay, so that one is a little bit more difficult to get to, but hopefully if your kind of mind is thinking the right way and you think, well, how am I supposed to know what element has this density? Try and think about using the units to work out how you've got, how they've got to that number, and use the clues in the questions such as the room temperature and pressure to figure out how you might be able to work out this answer. Okay, the next part of the question is slightly different. Now we're talking about, still talking about period 3, and this time they specified chlorides. Okay, and now we want to use the table to explain the properties that are shown in table 1 in terms of bonding and structure. So hopefully when you look at this table, you see a clear pattern between these first 2 here and these 3 here. Okay, so we see obviously the first 2 are from group 1 and 2 chlorides, and the last 3 are from group 4, 5 and 6. So we've got metal chlorides, and non-metal chlorides. And we can see that they've got different matching properties according to the colours I've highlighted. So the metal chlorides have poor conductivity in solids but good in liquids and high melting points. The non-metal chlorides have poor electrical conductivity in both solid and liquid and low melting points. So this question wants us to explain those properties in terms of the bonding and structure. So we want to first of all talk about the fact that NaCl and or MgCl2 are giant ionic lattices. Okay, giant is the structure here, ionic is the type of bonding. Giant kind of goes with the lattice. I don't think from the mark scheme that you'd be expected to necessarily write both words, but ideally you want to say ionic and giant lattice if you can, because that's talking about both the bonding and structure. Now you want to link that to the properties. So this means it's a poor conductor as solid. Why? Because the ions are fixed in place or cannot move to carry charge. Good conductor in liquid. Why? Because now the ions are able to move and carry charge. Or you could say that they're mobile, the ions are mobile in liquid state. I'm not sure if you actually need to write both of these things in order to get the mark, but just something that either combines both of those things into one, or just makes it clear that you understand why the ions are, the ionic compound is a poor conductor in solid, but a good conductor in liquid state. Then for the melting point, high melting point, because strong ionic bonds take a lot of energy. A lot of energy is needed to break the bonds. Okay, and then we just do the same thing for the non-metal chlorides. So silicon chloride, phosphorus chloride, or sulfur chloride, we'd say poor conductors because all covalent bonds. Covalent bonds mean that electrons are fixed in place and or cannot move to carry charge. Oh, I forgot to state the structure and bondings. Of course, these are simple covalent molecules. Okay, or you could say that they're simple molecular structures, but basically simple covalent molecules kind of covers both things. So just don't forget to mention simple is the structure, covalent is the bonding, so molecules is the structure as well. So right, so we said about the conductivity, so then the melting point, low melting point, because the covalent molecules held together by weak London forces, or you could say induced dipole-dipole forces. Just be careful here with terminology. Some people might have mentioned van der Waals forces to you, or you might still be talking about intermolecular forces that you might have learned at GCSE, but actually the mark scheme in this case will ignore anything other than London forces or induced dipole-dipole forces or interactions. So you want to specify what type of forces are holding those molecules together, and the fact that those are weak, which means, oops, that was supposed to be underline, which means it takes less energy needed to break molecules apart. Okay, and that's pretty much it. So 5-mark question, you do have to write quite a lot, but you can, there are ways to kind of try and make it more succinct. The key things in the mark scheme are to identify the structure and bonding of each type, mention why they are good conductors or bad conductors, and then compare the bond strength between the ionic bonds and the London forces, i.e. more energy is needed to break the ionic bonds than the London forces. Okay, looking at question 2 then. So here we've got reactions of hydrogen peroxide and cobalt-2 ions, and you've been given the equation here and told that the reaction is catalyzed by manganese oxide. Okay, so you may recognize this reaction as a reaction that you normally use to make oxygen gas. Hydrogen peroxide actually decomposes naturally, but this manganese oxide makes it happen much faster. We get given some volumes and things here. So we've got 50 centimeters cubed of hydrogen peroxide added, a small spatula measure of the catalyst. We don't need much because it does get used, it gets reused over and over again. As soon as we add the catalyst, the flask is connected to the gas syringe quickly. And then the student measures the volume of oxygen every 200 seconds. We get given a table of results, and then we want to process the results by plotting a graph of O2 against time, and then using your graph to find the rate of reaction in centimeters cubed per second at 500 seconds. So to save a bit of time, I've already plotted the graph here for you. So just to highlight what things they're looking for in the mark scheme, they're looking for just for one mark for the graph drawing. You need to correctly label the axis, and you need to have the volume on the y-axis, the time on the x-axis, with the correct units, so centimeters cubed for the volume and seconds for the time. So labels and units together. You want to use at least half of the graph paper in both directions. So ideally, rather than you could have potentially used one large box for the 10s going up, but ideally you want to use the maximum amount of space as possible. So having your y-axis go all the way up to 50 on the left-hand side is the best way to use the space here in this case. And then going up in 200s is a good idea on the x-axis, because you've been told that the measurements were taken every 200 seconds, and you've got enough space to fill it up to 1400, which was the last measurement. So, and then linear scales means that you're going up in even increments. So this is what the mark scheme says. So all those 4 things, correct axis, labels, units, linear scales, and using the maximum amount of graph paper is 1 mark. Then correctly plotted points gives you the 2nd mark. Ideally, you would put the point at the origin, because it did say in the table at 0, we had 0, but that wasn't actually required for the point. So we're looking for the correctly plotted points from 200 to 1400. Then you're looking at the curved line of best fit. So we want the curve that's drawn through the origin, and the curve not drawn with straight lines between the points. So we want a nice smooth curve that goes up in a smooth line. So that's 3 marks so far out of the 5, and then the question actually asked, as well as drawing the graph, to calculate the rate of reaction. So then you've got to calculate the rate of reaction, you've got to draw the tangent on the graph, which is the orange line I've drawn here, making sure that that's drawn at t equals 500, time equals 500, because that's what the question asked you for. So you're going to draw the tangent at that point, and then calculate the change in y over the change in x to calculate the gradient, which gives you the rate. So the way I calculated it, I got 50 minus 11.5, and then 950 minus 0. You'll probably get different range of marks, a different range of numbers, I mean. But if you do 50 minus 11.5, and then 950 minus 0, I got 0.0405, which gives me 0.041 if I want to do it to 2 decimal places, to 2 significant figures, but there's no specification on that. So I think whatever you write there is fine, as long as it's not, you know, ridiculous numbers of significant figures. And as long as your range is between 0.037 and 0.047, then you would have got the mark for that. Remembering everyone's going to draw the tangent slightly differently, so they do give you an allowance for a slight range there. Okay. Right, so the next question is asking then about the reaction in the equation 2.1. Now, for me, if I was doing this, this question, I would want to have that equation right here next to me because I want to use it in my calculations. So equation 2.1 they've given you, but I want to rewrite it. So 2H2O and 2. So 2H2O2. Okay, right, so the reaction proceeded until no more gas was evolved. The volume of O2 in the syringe is now 55 centimeters cubed, measured at room temperature and pressure. And again, that's a clue that you can use 24 dm cubed as the volume of 1 mole of gas in that. And now it wants you to calculate the initial concentration of the hydrogen peroxide. So the information we start with is the volume of the gas in the syringe, and using room temperature and pressure we can work out that the number of moles in that volume of gas. So we're going to find the number of moles of O2, which is the 55 centimeters cubed, divided by 24,000, which is our 24 centimeters cubed of gas in centimeters cubed. And that gives us 2.29 times 10 to the minus 3. So we're just using that relationship of 24 decimeters cubed is the volume that 1 mole of gas takes up at room temperature of pressure to work out how many moles of oxygen we had at that point. Now, using the equation, we want to identify the fact that for every 1 mole of oxygen, we have 2 moles of hydrogen peroxide. So this is a 2-to-1 ratio. So we want to times the number by 2 to get 4.58 times 10 to the minus 3. And that's going to be the moles of H2O2. Okay, so now we have the moles of the H2O2. We want the concentration. So we need the volume, which it did give us in the question here. So we've got 50 centimeters cubed. So 4.8, so moles, concentration equals moles over volume. So 4.58 times 10 to the minus 3 divided by 0.05 equals 0.092. And that's the answer there. So I'm just going to underline that instead of put that on the line. Okay, so the difficulty with this question was really just making sure that you can identify where to get the values from that you needed to actually put in the calculation. But again, they do give you enough clues in the question, and sometimes you have to flip back a couple of pages to the list of information that they gave you initially in order to find all the information that you need, but it is all there. So if you're completely stuck, then my advice is to go back to the beginning of the question, read through the information again, because you'll often find something that perhaps you missed or forgot that was there. Okay, the next one then is about electropotentials or redox reactions. So it's still on the same reaction, hydrogen peroxide, or similar anyway, saying it can act as an oxidizing agent or as a reducing agent. We've got some electropotentials here, and remember that electropotential is always given in the reduction form. So these are all reduction reactions. And then you want to use that information to write an equation for a reaction in which hydrogen peroxide acts as a reducing agent. So reducing agents reduce other things by being oxidized themselves. So we want to look for where hydrogen peroxide is oxidized. Okay, so looking at the equations above, we have hydrogen peroxide here and here. As I said, the forward reaction is the reduction reaction. So this reaction we're going to cross out because that's going to be hydrogen peroxide being reduced. In order to have hydrogen peroxide being oxidized, we want to reverse this equation so that we've got the hydrogen peroxide being oxidized, therefore reacting as a reducing agent. And then okay, it doesn't tell us which of the bottom two equations to use. Okay, but if we think about the electrode potentials for a second, if we had the reverse of this, which would be minus 0.68, and this equation here, we would have a negative electrode potential value, which means that reaction would not be feasible. So we can also cross out this, because this is not going to be a feasible reaction with the hydrogen peroxide that we chose. Just double checking this 1.51. If we add that to our minus 0.68, then we will get a positive value, which means that the reaction is going to be feasible. So we're going to use this reaction, and now all we've got to do is balance the two together by making sure we've got the same number of electrons in both. So we're going to times this one by 5 and this one by 2, so that we get 10 electrons on both sides, and that we can cancel those out. Okay. So now, remembering to write the top one backwards, I'm going to start with the MnO4, MnO4 minus plus 8H plus. I'm going to ignore the electrons because we've already cancelled them out by making 10 and 10. So plus 5H2O2, because that should be on the left-hand side. We've reversed the equation. Okay, and then going to oh, that's supposed to be 2. Sorry, I didn't times it by 2. That's supposed to be 16H plus. Right. So 5Mn2 plus 8H2O plus 10H plus 5O2. Okay, and now we can cancel out some of these. Okay, so that leaves 6H plus. And let me just double check. I think that's it. So 2MnO4 minus plus 5H2O2 plus 6H plus goes to, oh, I don't know why I wrote 5 here. This was supposed to be 2. This was from this equation. So that's 2 plus 8H2O plus 5O2. Yeah. That's the correct equation. Hopefully you can see how I got that. It does involve quite a bit of work in the first place to just remember how the electric potentials comes into this and which of those two equations either side to use. But the key thing to remember is that you need to reverse the H2O2 equation in order to make that an oxidation reaction. Please let me know if you do have any questions as we go along. Okay. Right, now this one is, it did say at the beginning of the question this was about hydrogen peroxide and cobalt. So far we haven't looked at cobalt, but now they're finally getting into it in question 3. I'm not really sure why they don't just have this as separate questions, but anyway, I guess that's just how they do the unified chemistry questions. Okay, so we've got cobalt 2 forming complex ions with water ligands and chloride ligands. It's telling us that with water ligands, it's a pink octahedral complex, giving us the formula there, and with chloride ligands it's a blue tetrahedral complex ion. Okay, so the octahedral and tetrahedral gives us some clue as well about the formulae, even though they gave us the formulae. The first one there, the tetrahedral, does give us a clue, because octahedral complexes usually have 6 ligands around the outside, whereas tetrahedral complexes have 4. So this gives us a clue about the change in coordination number when a reaction takes place. Okay, so students dissolve cobalt sulfate in water in a boiling tube in a pink solution of forms. Okay, so that makes sense according to what they've said. The water ligands give us a pink solution. I'll just actually write that in pink, and I probably should have written the other one in blue, but okay, let's change it to blue for fun. Funsies. Okay, so experiment 1, student places the boiling tube in a water bath at 100 degrees. Concentrated hydrochloric acid is added dropwise, and the color of the solution changes from pink to blue. Okay, in experiment 2, the student places the boiling tube from experiment 1 into an ice water bath at 0 degrees centigrade, and the color of the solution changes from blue to pink. Okay, so we've got 2 things going on there. We've got different temperatures in the 2 experiments, and we've got hydrochloric acid being added in the first one, and then in the second one we've got the reverse color change happening. We're not adding or removing any concentration of anything, but the reaction is reversed. So first of all, write the equilibrium equation for the reaction that takes place when the color of the solution changes. Okay, so We've already been given the formula for the water complex, which is up over here. So we just need to copy that. Okay, and then we were told we add hydrochloric acid. So you can either add the hydrochloric acid or you can add just the chloride ions. Usually it's more common to add the chloride ions, but like you said, you can add the hydrochloric acid instead. Okay, make sure you do a reversible reaction because we know this is an equilibrium equation and that this can go back and forth. Okay, then it turns into the cobalt chloride complex. And as we said earlier, this is a tetrahedral one, so it only has 4 ligands attached to the outside. And we also have a change in charge from 2+ on the left-hand side to 2- on the right-hand side. So that's all important things to include. And then we've got 6H2O, because the 6H2Os were bumped off of the original complex. And if you did write 4HCl, then you need to also have the 4H+ over here to balance the equation. Okay, so this is our ligand substitution reaction where the coordination numbers change from 6 on the left-hand side to 4 on the right-hand side. So we just need to have the 4 ligands that were attached to it on the left-hand side, and then the 6 that were taken off on the right-hand side. Okay, explain the observations and predict whether the formation of the blue color is exothermic or endothermic. Okay, so here we want to focus on the temperature changes. So here we've got a hot temperature and it's going from pink to blue, and here we've got a cold temperature and it's going from blue to pink. Remembering this is the pink one and this is the blue one. Okay, so in the first experiment, we added hydrochloric acid and it was at high temperature, and that made the blue color. And that suggests that the forward reaction is endothermic, because by heating it up, we're pushing the reaction forward in the forwards direction towards the right-hand side. When we cooled it down, the reaction changed from blue to pink, which just as we cool it down, the reaction is going to do the exothermic direction, which is the backward reaction. So I think from just the temperatures, we can work out that the forward must be endo and the backwards must be exo, because if you heat it up, it favors the endothermic reaction. If you cool it down, it favors the exothermic direction. So just try to associate the color changes that they've explained to you with the changes in temperature. So the enthalpy change of the formation of the blue color, which is the forward reaction, I would just write forward reaction, is endothermic, because the equilibrium shifts to the right at high temperature, 100 degrees C, or you can say the opposite, that it shifts to the left at a low temperature, 0 degrees C. So the mark scheme just says to me to take care that the direction of shifts depends on the direction of equilibrium that you wrote the equation in. So because I wrote the equation with the pink on the left and the blue on the right, then the formation of the blue is the forward reaction and endothermic. But obviously you could have got the right answer by writing the equilibrium equation the other way around, because it's obviously an equilibrium equation, so it would have been fine the other way around. But in that case, you just need to specify that the pink to blue change is actually the backward reaction in that case. So just be careful about making sure you associate your answer with the information that you've actually written down in the equation. So question 3, overall, right, the question is about ethane dioic acid, COOH2, and ethane dioate ion, COO- 2. The ethane dioate ion shown below can act as a bidentate ligand, and it's given us the shape of the ligand. Fe3+ forms a complex ion with 3 ethane dioate ions, and the complex ion has 2 optical isomers. So they're giving us quite a lot of information here, which is useful for us in our workings out. Draw the 3D shapes of the optical isomers, and in your diagrams show the structure of the ethane dioate ligands and any overall charge. Okay, so we want to draw the 2 optical isomers I would go about this by just splitting this space into two. And my optical isomers need to be mirror images of each other. So I'm going to draw one, and then I'm going to draw the second one as a mirror image of that first one. So Fe, and it's going to have an octahedral shape. So I'm going to draw the lines on, first of all, without drawing any of the ligand, because I think it can get quite confusing if you start trying to draw a ligand on before drawing the bonds, because then your 3D shape kind of gets a bit mixed up. And actually, since we're going to do an optical isomer, I'm just going to copy that. Apologies, you can't do that on your piece of paper, but it's handy to be able to do over here. Okay, so now it doesn't really matter where you start with the ligands on the first one, as long as you then do the mirror image on the second one. So remember that the position of the lone pairs that produce the bond, the dative covalent bond, are these O- areas here. So we're going to put that O there, that O there, join them up like that, and then the double bond O like that. Okay, then the same here, O, O, join them up, double bond, O, O, join them up, double bond. Okay, and now we're just making sure to do the overall charge. Now we've got Fe3+, and then we have 3 2- ions. So we've got 3+ and 6-, which gives us 3- overall. The overall charge is 3-. Okay, so that's going to be the same for the other one as well, but I will wait until we put the ligands on before I draw that. Okay, so mirror image now for the other one. So we're going to go 0 or 00, sorry, connect them with that structure, double bond O, and then O, connect them again. Oops, O, connect them. Let me just rub that first mistake out. There we go. Double bond. Okay, and then the brackets, overall charge 3-. Okay, so you get 1 mark for each isomer, and 1 mark for showing that the charge on the overall ion is 3- as well. The bonds must go from the O ligand atoms on each structure, and you do need to show the full structure of the ethane dioate ion that you've been given. Okay, then to go on, ethane dioic acid is present in rhubarb leaves. The student carried out a redox titration including aqueous cerium sulfate to determine the percentage by mass of ethane dioic acid in rhubarb leaves. In the titration, Ce4+ ions oxidize the ethane dioic acid in hot acid conditions, and you've been given an equation here. Okay, so that's the oxidation of the 4+ ions, and it tells us that those C4+ ions have a yellow color, whereas the C3+ ions are colorless. So it's already told us the color change that you're going to see in this reaction. The student weighs 82.68 grams of rhubarb leaves and extracts ethane dioic acid from the leaves. The ethane dioic acid is added to dilute sulfuric acid to form a colorless solution, which is made up to 250 centimeters cubed with distilled water. Okay, so by adding the ethane dioic acid to the sulfuric acid, we've got a colorless solution, which is becomes our standard solution in the 250 centimeters cubed of water. So remember, we've got whatever the mass that we weighed here at the rhubarb leaves, there was a certain percentage of that was the ethane dioic acid. We're going to eventually work out from the titration how many moles was in the titration. Then we need to work out how many moles was in the 250, which was the sort of the standard solution we made up, and that will tell us that the number of moles in the 250 will be related to the number of moles we had in the original mass, and that will give us our percentage by mass. Okay, so the student heats 25 centimeters cubed of this solution. So we've taken a tenth of this. So in order to get back from the titration later on, we're going to need to times it by 10 to get back to that. Okay, so they heat it to 70 degrees centigrade and then titrate that volume with 0.5 mole per decimeter cubed of this, the cerium sulfate that we had above. And just note that this cerium sulfate, given this equation, given this formula, this is our 4+ ion, which should be the yellow colour. Okay, the student repeats the titration to obtain concordant or concordant consistent titers. All right, so before we go into the actual table, the first question says the titration is self-indicating and the solution doesn't need to add indicator. What colour change would the student observe at the end point? So, right, we know that the solution started off as colourless, and then the solution that we were adding to it from the burette is yellow. So eventually, we're going to have the yellow colour in this titration. So yeah, it starts off as a colourless solution in the flask, and then as we're adding this yellow substance to it, we're going to end up with the yellow colour once all of the acid has been used up. Okay, calculate the percentage by mass of ethane dioic acid in the rhubarb leaves and give your answer to the appropriate number of significant figures. So, like I said, we have to work backwards from the titration here. So first step is to find the mean titer. So you've got to take the differences here to find the actual titer of each one. So this one's going to be 23.25. This one's going to be 23.50, and this is going to be 23.15, I believe. Yes. Okay, so the concordant results are this one and this one. So our mean titer is going to be 23.25 plus 23.15 divided by 2, which gives you 23.2. You don't have to have the 0 there, but you can, and that's obviously in centimeters cubed. So that's our mean titer. Okay, the titer was the thing in the burette. Remember over here was the Ce4+ ions. So the moles of the Ce4+ ions will be the volume times the concentration. Okay, so the concentration is here, 0.05 moles per centimeter cubed. Okay, so the volume is 23.2 divided by 1,000, remembering to always convert to decimeters cubed, times by 0.05, that was what we just got, wasn't it? Yeah. And that gives us 1.16 times 10 to the minus 3. Okay, so now from the equation, we have a 2-to-1 ratio of the cerium ions, oh gosh, right, to ethane dioate ions. So we're going to 2-to-1 ratio. So the moles of COOH2 equals, so yeah, 2-to-1 ratio of the cerium to COOH2. So divide that by 2 to get the moles of the ethane dioate. And that is the answer for that, 5.8 times 10 to the minus 4. This was in the 25 centimeters cubed portion that we put into the solution. So that was here. So now you need to times that by 10, as I said earlier, to see how much was in 250. So that's going to be 5.8 times 10 to the minus 3. And then find the mass of the ethane dioate that was in the original rhubarb. So we need to find what's the MR of COOH2, and that it should be 90, if I'm correct. So then we do the moles times the mass to get, sorry, moles times the MR to get the mass. So 90, sorry, 5.8 times 10 to the minus 3 times 90 gives us 0.522 grams. That's how much mass of the ether and it was in the original rhubarb. And then the original rhubarb was 82, where was it? 82.68 grams. So we do 0.522 divided by 82.68 times by 100 to get our percentage, and that gives 0.631 cent. And I'm not sure exactly what the calculator value is because I've just not just done this on the calculator. I wrote down my answer earlier, but whatever the calculator value is, you need to make sure that this is expressed to 3 significant figures. Okay, it says in the answer in the question here to appropriate number of significant figures, so it is important that you do that. If you're ever questioning what the appropriate number of significant figures is, it's based on what the minimum significant figures are given to you in the question. So you should find that in all of the values you're given to earlier, they've given them all to you in 3 significant figures at least. So that's why you choose 3 significant figures for this. Okay, and so that's the end of that question, and we've pretty much come to the end of our time. So thanks again for watching and joining us, joining live if you did join live. If you're watching the replay, then obviously feel free to rewind this and go back as much as possible. You can always download a mark scheme for this paper on the OCR website, just as I sent you the link to the paper itself. If you've got any other questions that I didn't cover today about these questions, so if you've got any clarification questions of things that I didn't mention today, then please feel free to leave a comment in the website comment box, or you can send a message to chemistry@boostrevision.com to ask any of your questions in case you didn't have a chance to ask them on this live. So thanks again for joining. I'm going to stop the share there. Hopefully you found this useful. We also are open to any suggestions. I know this time is a kind of a bit of a difficult time with things changing all the time in the UK and around the world with coronavirus. So do let us know how we can support you. Send me an email, chemistry@boostrevision.com or ligaya@boostrevision.com, and we'd be happy to adjust the sessions that are coming up to suit your needs, because obviously the exam has been cancelled. We're not going to be you're not going to be studying for the exams in the way you normally would have done, but hopefully you are still working towards something, whether it be your teacher assessments, whether it be your university courses. I hope you're using the time productively. I hope you're not getting too stressed or whatever about the situation. Just stay home, be safe, wash your hands, all that kind of stuff. And yeah, Dr. Rusu will be back on Sunday with some more questions focusing on organic chemistry this time. This one was mainly focused on physical and inorganic. So join Dr. Rusu on Sunday at 1 p.m, I believe, UK time. We'll send an email the day before to double check that time. And he'll go through some more sort of past paper questions as well to help you guys with your revision for next week's assessment, or any of the assessments that you've got coming up. So feel free to get in touch. We're also on Instagram @BoostRevision. And there are videos on YouTube as well as on our website, so please check those out as well for any further help that you may need. So thanks again for joining, and hope to see you again next time. Bye.